And Mike, Houston's with you on 2. Just FYI, we know you're doing the food cleaning procedure. You can skip step 2 for the brake coat item on there. We're actually going to add brake coat tomorrow after we install the seal, so no need to do that today.
You guys are awesome. Thank you for thinking ahead. We are pretty pristine here, and I think this seal would be a great addition to our lab hatch family. I'm working on a few of the metal parts real quick. So no further food stains, and then we'll get straight to the procedure for loosening and then readjusting the hatch seal. Thank you.
All sounds great. Thanks, Mike.
an airlock on Space to Ground 2.
We're with you, Mike. Go ahead.
And I'm with you on the hatch seal R&R procedure, 1.2.505. And looks like we got a lot of step 1 done already with the cleaning. And I'm about to join you with step 1.3. And please, along the way, you guys are full participants. And if I'm doing something that's wrong, or as you've been doing, you have some good advice to help along, just please let me know.
Copy that. Absolutely, we will. Thanks for all your help on this, Mike. And while I've got you on here, for your wayward piece of foam that you found right there, you can just throw that away in the foam trash. And there's a couple of those CTBs in the airlock if you want to, and I can give you those details if you need.
I know exactly where it is, Scott. Thank you very much.
Copy that.
airlock on 2 for a quick question. Fasteners that I am loosening and then disengaging on the adjacent seal segments, step 1.6. I'm assuming those are captive fasteners?
Affirm, Mike, all of the fasteners are captive.
Station on spacecraft 2 for Lex.
William 2, Kimia-san.
Okay, I'm just checking the status for the checkout. And if you need more time actually for the checkout, I can start series exercise now, and I can delay the checkout activities later. Then you have more time for the checkout. So how checkout proceeding?
Thank you, Miss-san. Thank you for checking. And yeah, unfortunately, the ground checkout is taking much longer time than we expected. So yeah, we like your idea. So you can start your exercise first, and then after that, we may ask you to perform the JLX install part 2 activity.
I understand the situation. During the exercise, I think my exercise will also end early. So if you guys ready to close out, please let me know without any hesitation, anytime. Thank you.
Copy that. Thank you very much for your consideration.
station Houston on 2 for Mike and timeline.
Go ahead, Houston.
Yeah, a couple things, Mike. So first of all, would you mind relaying to Johnny and Zena on here? We're switching over the Dragon comm over to 2 since we're in a KU LOS right now, so they can call us on 2 if they need anything. And then for you, to help out with your timeline, wanted to give you an option here. We know you have that CMS conference coming up. If you would like, we're willing to, after you get done with the seal removal, you can move directly into your midday meal, and then we could pick up that conference starting around 0900. Wanted to see what you thought about that. Oh, I apologize, 1400. Wanted to see if you'd like to take us up on that offer.
If you don't mind, that way we can give full attention to our seals, and then be very happy to meet the ARED team at 1400. Thank you.
And Dragon copies as well on the comms.
All right, that sounds great. No problem at all for you, Mike, and copy you on 2, Zena. Thank you.
And Houston on 2 from the airlock.
Go ahead, Mike, with you on 2.
Yeah, it's too bad you're not with us visually. The seal came right off. Compliments to Oso and the rest of the team for a really nice procedure. So I inspected both sides of the seal surface, the seal itself, and then you asked me to take a look at the bulkhead. The bulkhead looks a little bit like it has a very, very thin layer of brake coat on it. I'm not sure it needs to be cleaned, but aesthetically it could use a touch-up with a lint-free wipe, I think. So that is my step 1.13.
Copy that, Mike. That's good news right here. Stand by for another word. Give me 1 minute. Yeah, Mike, back with you on here. So, yes, we're happy to take you up on the offer to clean the bulkhead up a little bit if you think it's dirty. Thanks for offering that right there. And just to let you know, about under a minute for a 15-minute LOS, so we'll just catch you on the other side. Thanks for all the help with everything.
Our pleasure, and I will continue on with the procedure. We'll clean up the bulkhead and reinstall the seal, the seal plate. And if I get stuck anywhere, I will stop and wait for LOS or AOS. Thank you.
Sounds great. Talk to you in a bit.
the station on 2. Looks like you're back with us.
And we're back, Mike. Go ahead.
I'm pleased to report that the hatch seal replacement after taking it off and cleaning the bulkhead and putting it back on, that went as nice as it possibly could have. And we followed the rest of the procedure. And just to let you know, it looks good, but you can be the judge of that. I'll send down a whole bunch of before and after photos. Do you have any questions? And I do have one more thing to say.
Copy that, Mike. Stand by 1. I'll have one question for you. Yeah, Mike, that is all great news. Thanks for that. We did have one follow-up. We're wondering if you had any observations on the fasteners, whether or not you were seeing any residue from the Loctite.
Yes, there was a little bit of, I don't say almost dust, small, a couple now and then, small particles from Loctite from, I guess, the original installation. So those kind of just gently floated out of the way and removed themselves.
All right, that's great news. Thanks for that right there. Also, one go back. Could you let us know how many of those lint-free papers you use so that we can, 2, got it. Copy that. Appreciate that. And with that, we're ready to copy your other item.
Yeah, I think that was part of it, was 2 lint-free wipes, so we're on the same page. That's good. And then just to make sure we're very transparent here, the way I read the procedure was, right now I have 14 fasteners that are not attached because we got the ends and the center of the seal tightened down. So we are good to go for tomorrow, but I just wanted to make sure that you guys were on the same page with that.
Copy that. Always good to clarify with us, but that is the exact config we wanted in, so appreciate all that, Mike.
Yeah, no worries. And just to let you know, while we were talking, I looked at all the fasteners that are still sticking out, and they are pristine clean. So there's no Loctite residue on them. I think any Loctite liberated itself in forms of very small dust particles. And I personally think we're good to go for tomorrow, and that was about as good as you could expect, thanks to Oso and the Mur and the rest of the team.
All right, excellent. Great words. We think we are also good to go, so appreciate all the help this morning on that, Mike.
All right, fantastic. And with that, I will finish up the procedure, clean up the work site. Do you need the airlock camera anymore?
No longer needed. Appreciate you letting us spy on you this morning.
I felt a lot better having my friends help me along, so thanks, everyone.
Always a pleasure.
Houston Station on 2 for Dragon.
Station, Houston, on 2. Hello, Zina, go ahead.
Hello, Johnny and I finished up the Dragon Emer transfer part 2 with the exception of the extra PFD in the final step of that procedure. Location 11 in Dragon is completely full. It still has a bunch of the common bags for our uphill meals and water. Should we remove any of those bags in order to install the PFD in location 11? Does that match what the ground is expecting?
Zina, we copy your question and we'll get back to you as soon as I have an answer.
Copy, no problem. It's currently tempstow just above location 11, and we'll be ready when you are.
Station Houston on 2 for Xena and Dragon.
Ready on 2.
Hey, Xena, trying to come up with a plan for your question. We really want the extra PFD to go in location 11. We would like to understand how much you would have to remove in order to fit that extra PFD.
I can double check. I didn't remove anything from location 11 in my assessment. It just looked like it was already nominally full with the expected number of common bags, but I can take out the common bags, do a survey of how many are in there. Maybe we can fit it. It would be tight. If we have to remove one, it would just be one common bag.
Xena, down here, we would love to have that survey of common bags needed and on your own timeline.
Will do. Houston, Dragon on 2 for PFD.
Go ahead on 2, Zina.
We did an inventory of the common bags in location 11. There actually were only 5, so I just tried harder and fit the PFD. I would not say that this is a quick access, so if we did find ourselves having to undock in a 5 config, wondering if there would be a step to move that elsewhere or if we should just know this in advance.
Hey, Zina, thank you for that assessment and for fitting the extra PFD. The assessment down here is that is the final configuration. We just want to make sure that the PFD is the first thing that you access when you open that location. And then we're counting also on your awareness of that position.
Yeah, affirm, it is the first item accessed when you open location 11. It is in location 11, position 4. It's just very tight and also fastens under strap alpha, and it takes quite a bit of tugging to get that common bag out and then get the PFD out from within that common bag. So we'll think about our unassisted egress procedures, and we'll go from there.
Zina, do you think if you took one of the common bags out, would it make it easier to pull out that PFD?
I do, yes, and I think specifically either the bag in position 2 or position 3. If we removed that, it would make it much easier to access the bag that is the PFD now in position 4.
We copy, Zina. Thank you for that assessment.
Einstein once wrote an introduction to a book on astronomy. He mentioned this idea, he called it an idea of pure genius.
This is Terence Tao, one of the world's most renowned mathematicians. What he's referencing right now is how Kepler deduced the shape of Earth's orbit, which was astoundingly more clever than I had realized. But I'm getting a little ahead of myself. A lot of math enthusiasts will be familiar with Tao as a story of prodigy turned prodigious mathematician, but one of the most remarkable features of his career is how collaborative it's been, spanning an unusually wide breadth of topics within math. I had the chance to sit down with him, and I asked if there were any topics that he believed would benefit from some strongly visual presentation, and I fully expected an answer from pure math, but I was pleasantly surprised when he proposed instead a story of cosmic distances. It's the story of how humanity first figured out the sizes of objects from the size of the Earth to that of the solar system on up to the universe, and how each measurement unlocks a path to the next one.
I always liked astronomy as a child, just found like red dwarfs and neutron stars and so forth fascinating, you know. Yeah. And I had a little telescope. As a kid, I just read all these books and said, you know, the distance to Mars is 18 million miles or whatever, and I just sort of accepted, oh, they figured out some way to do this. I never knew how they did it.
Science communication at its best is, to me, less about presenting facts in a memorable way, and more about showing how it is that we know what we know. When it comes to cosmic distances, it's very easy to be awestruck by the sheer unfathomable scales involved. But what deserves just as much awe, and is much less commonly highlighted in pop science documentaries, is how clever the reasoning can be at each step.
And I realized, oh, it was always some mathematical trick. And it was always a cool trick. Like if you want to measure the distance to x, you can never just look at x. You have to look at y and how x impacts y. So the idea is clever, and then you have to have data, which needs technology and so forth. But then it's just mathematics.
In this video, we'll cover the steps of the ladder up to the planets, that moment of sheer genius that Kepler brought. And in the next part, we'll continue on up to the most distant galaxies. The very first measurement of the ladder is the radius of the Earth, a somewhat classic tale. But to even ask this question presumes that the Earth is a sphere, or at least roughly spherical, so you might wonder how the ancients first deduced the shape of the Earth.
The first really convincing proof came from the moon. And this is the constant theme in the distance ladder. If you want to measure one object, in this case the Earth, you have to use a reference object that is some distance away. See, the thing is that we're stuck on the Earth. Okay, like if we could step away, if you look from many different angles, you could see that it's round. If you only saw it from one angle, it could be a flat disk. Flat disk, if you look at it from a different angle, it would look like an ellipse. But you can actually prove there's a nice little geometric argument actually that if there's a convex body and every single projection is a circle, then it has to be a sphere.
I'm going to guess that most of you find this pretty intuitive. After all, if every shadow of a given shape is a circle, what could that shape be other than a sphere? But of course, a mathematician always keeps a keen eye out for those strange counterintuitive exceptions, and he shared with me a nice proof of this fact after the interview, which I'll link to in the description.
In 2 dimensions, what I just said is not true. You know, so there are 2-dimensional shapes which every projection is an interval of the same length, but they're not round. Okay? But in 3D, there's enough perspective, as it turns out. If you could look at the Earth and you could always see that it was round, that tells you the Earth is a sphere. NASA can do this, okay, but Aristotle could do this, and he used the moon because he knew about lunar eclipses. Lunar eclipses happen when the moon falls onto the Earth's shadow, and the Earth's shadow, as you can just visibly see, it's always a circular arc. So there's a picture I can show you. This is not my photo, but someone took several images of the moon entering and exiting the lunar eclipse, and it composited them together into a single shot. You can see the shadow of the Earth. This is visible proof that the Earth is round. And you don't need telescopes, sextants, spacecraft. You just need to look at the moon.
Something else very cool revealed by these kinds of compositions is how you can just see the relative size of the Earth and the moon. We'll get to that in a moment, but first things first, how do we figure out how big the Earth is?
The first person to do this that we know of is Eratosthenes. The way the story goes is that he had read somewhere of this well in this town called Syene, where on one day of the year, the summer solstice, you could look down in the well and you could see the sun reflected in the water underneath. And he said, oh, that's kind of cool. I don't live there, but I have a well in my own town, Alexandria. I'm going to go try the same thing. So he waited until the summer solstice. At noon, he went down and looked at the well, and there was no reflection of the sun. So I think, like, if you're a regular person at this point, would say, oh, you know, that story is fake news or whatever the film was at the time. Sure. And he knew from Aristotle and the others that the Earth was round. The reason what was happening was that the sun was not actually vertical.
Let's think of the sun as far enough away from Earth that all of its rays of light are effectively parallel. At any given moment, if you draw a line from the center of the Earth straight to the sun, It passes through some point on the surface, which must be experiencing this phenomenon, where the sun is directly overhead. But if you were someone in Eratosthenes' time, it would be very difficult to know exactly where this was happening at a given moment. So what makes the summer solstice special is that on that day, the axis of Earth's rotation is tilted directly towards the sun. And as a result, on this day, as the Earth revolves around that axis over 24 hours, there's a consistent line of latitude where all of the locations on this line predictably experience this phenomenon, where at high noon, it's the highest of all high noons, where the sun is overhead. This line has a special name, it's called the Tropic of Cancer, and the town Syene that Eratosthenes had read about sits on this line. Now Eratosthenes himself was a bit further north than that, in Alexandria. So on that day, at exactly noon, the direction he perceives as straight up, which I'll draw with a pink line here, is not pointed towards the sun. It sits at some angle with all of those rays.
He had what's called a gnomon, which is kind of like an ancient protractor or sundial, a portable sundial, basically. He measured that the sun was actually about 7 degrees off of the vertical.
Critically, because he could also know that at this exact moment, down in Syene, many, many, many miles away, the sun was directly overhead, he deduced that this means the arc length along Earth between Alexandria and Syene is about 7 degrees. This in turn means the ratio between 7 degrees and the full 360 degrees of a circle must be the same as the ratio of the distance between those two towns and the full circumference of the Earth. Now keep in mind, in the records that we have, it's not like he's reporting this distance in miles or kilometers. The units they were using back then were stadia, where a single unit is something like the length of a stadium.
So the distance was about, it's 5,000 stadia, which is about 500 miles.
How accurate is our conversion between stadia and miles?
That's a good question. We are not completely certain. So with the conventionally accepted conversions, I think the accuracy of Eratosthenes' estimate is about 10%.
You can find sources online that claim his estimate was more accurate than this, but just keep in mind if you selectively choose which of the many possible conversions between stadia and miles to use, you can kind of p-hack your way into a better number here. Still, 10% is pretty good with no technology, but of course all of this hinges on actually knowing the distance between these two towns. So the natural question you might ask is, how would he know that?
This is not recorded. There are some theories. One is that there are merchants that go up and down the Nile, and they know that in a certain day that their sailboat can travel so and so many stadia, and it takes so and so many days, X to Y. Yeah. And so from that, they have some estimate. The joke is that he basically hired what we would now call a graduate student to pace the distance from Alexandria.
Carefully counting the number of steps.
That 5,000 stadia is the only direct measurement. Just from that one graduate student, you can actually get all the way to measure the diameter of the universe. Right, now that's not actually what we do nowadays. I mean, because the errors stack up, but in principle, you could do that.
If you have a sense for how big the Earth is, one of the first cosmological distances that you can deduce from this value is the distance between the Earth and the Moon.
You can use eclipses again. So shadows are what let you observe things from a different location than the Earth. When you have a lunar eclipse, so when the sun is over here, the Earth shadow has size basically twice the radius of the Earth. It's a little trickier than that. There's something called the penumbra and the umbra, okay, but as a first approximation. Lunar eclipses, they last no longer than 4 hours. And this they knew from many, many observations. The moon actually takes one lunar month to traverse its orbit. And so, again, by taking the ratio between 28 days and 4 hours, you can work out the relation between the distance to the moon and the radius of the Earth.
To be slightly more accurate, during the full eclipse between first and last contact, the distance that the moon passes through would not only be those 2 Earth radii, but it would also include 2 moon radii. So if you want to measure how long it takes for the moon to traverse 1 Earth diameter in space, it might be more like the time between the first moment the moon hits the shadow and the first moment that it starts to exit it. Another thing to keep in mind if you were to go out and try this yourself on the next lunar eclipse is that lunar eclipses don't necessarily go through the center of Earth's shadow like this. So the measurements that the Greeks would have had to use would be with respect to the longest known eclipses. In either case, the slightly more accurate number to put in here would be more like 3.5 hours. And then when you work it out, this ratio between the length of a lunar month and the length of a lunar eclipse, all divided by pi, would tell you how many Earth radii away the moon is.
Aristarchus did this. It measured that the distance to the moon is about 60 Earth radii. And actually, the orbit varies between like 58 and 62 or something. So actually, it's really good.
As good as you could hope.
Yeah.
I brought up earlier how with these lunar eclipses, you can see the relative size of the moon and the Earth. The moon is about a quarter as wide as the Earth is. Now in practice, it's difficult to make this a precise measurement without photography. So the Greeks had a different way that they could deduce the size of the moon. Next time you see a full moon rising, try to measure how long it takes. What you should find is that it's around 2 minutes. What you're watching is not so much the moon moving through the orbit. Instead, it's that as you and the Earth are rotating, your line of sight over the horizon is scanning over the moon.
The moon basically takes 24 hours to cycle around the Earth, at least as observed by us because of the Earth's rotation. Actually, it's slightly less because the moon's also moving, but basically 24 hours. And so therefore, you can work out the ratio between the radius of the moon and the distance to the moon, just by taking the ratio between 2 minutes and 24 hours.
So because they knew the distance to the moon, they could use this to figure out the radius. Now keep in mind, both of their estimates could be at best approximately true. Since the real orbit of the moon is an ellipse, it's not a perfect circle. But the point is that with almost no technology, they had pretty decent estimates for the size of the moon and how far away it was.
The sun was trickier. So at the time, they thought the sun went around the Earth, but it actually doesn't matter for the argument whether the sun goes around the Earth or the Earth goes around the sun. Again, there's these two numbers. There's the size of the sun and the distance to the sun. You can compute the ratio again because of eclipses. And there's this weird coincidence. I mean, there's no reason why it should be true, but when there's a solar eclipse, the moon and the sun are almost exactly the same size. Yeah. I guess it's not true for lunar eclipses. For lunar eclipses, as we saw, Earth's shadow is much bigger. But for some reason, they are almost the same size.
What this means is that if you look at the ratio between the radius of the moon and the distance that it is away from the Earth, which is what determines how big it looks to us up in the sky, because of this solar eclipse coincidence, that has to be the same as the ratio between the radius of the sun and its distance away from the Earth. As we saw, the Greeks already knew that ratio for the moon. The point is that they could get at least an approximate sense for the size of the sun if they could figure out how far away it is, or vice versa. Now, the animation I'm showing right now is very grossly not to scale. You and I both know that the sun is actually much, much farther away than the moon is. But of course, that's not obvious when you just look at it in the sky. And so you might wonder, how could you conclude that it has to be so far away? In ancient times, for all people knew, seeing that it was roughly the same size as the moon in the sky, it could be, say, twice as far away as the moon is and only twice as big. In fact, for the animation, I'm going to go ahead and leave it unrealistically close like this, because it helps clarify how the next logical step works.
How do you work out the distance to the sun? You again use the moon. It's almost the only available object you can use. But you do something else. You look at phases of the moon. The sun illuminates half of the moon. And so we on Earth, we also see half the moon, but it's a different half. And so because of that, we get phases of the moon. This is also, by the way, why we know the moon is round. If the moon was flat, we would not get phases. We would get either a dim moon or a lit moon, but we wouldn't get these phases. So sometimes you get a full moon. If the moon is over here, you see the whole lit thing. Sometimes you get a new moon over here, and sometimes you get a half moon.
You can pretty much rediscover for yourself a way to estimate the distance to the sun by asking when exactly a half moon occurs. From the name, you would guess that it's halfway between a new moon and a full moon, but that's actually not true.
Half moon occurs not when the moon and the sun make a right angle at the Earth, but actually when the Earth and the sun make a right angle at the moon. Hopefully your graphic will be better than the one I'm drawing here. Okay.
Hopefully this makes some sense. For us to see a half moon, it means that the side of the moon that we see facing us overlaps by exactly 90 degrees with the side of the moon being illuminated by the sun, which in turn means we have a right angle at the spot labeled here.
As your lovely illustration will show, half moons are slightly closer to new moons than they are to full moons.
Of course, in this graphic, the effect is very exaggerated because the sun is being drawn so close to the Earth. How far away the sun is determines when exactly that half moon occurs. The farther away, the closer it is to the true halfway point. In fact, you can make this a little more quantitative, where if you measure the angle separating that halfway point between new moons and full moons from the point of a half moon, which again is confusingly not the same thing, then intuitively you can see how a smaller angle means a larger distance to the sun. And more precisely, when you do the little bit of trigonometry here, you can conclude that the distance to the sun is the same as the distance to the moon divided by the sine of that angle.
This is where the Greeks started hitting a wall of technology. What they did is that they knew that the moon took 28 days to go around the Earth, and so they had to measure exactly when a half moon occurred and what the deviation is. Now Aristarchus, he thought that the distance was 6 hours. The half moons occurred 6 hours before the midpoint between new moon and full moon. He doesn't write how he came up with this. And it's wrong. The actual discrepancy is half an hour. He's off by a huge factor. So the thing is, well, we have clocks, which work in the dark. They had sundials and which don't work in the dark. They also did not have telescopes. Mathematically, the method was sound. Technologically, it was just not possible for this method to work. No, but it worked well enough. Okay, so he was off by basically a whole order of magnitude. He thought that the sun was 20 times further away than the moon.
The true answer, based on the slight change to that angle that he was trying to measure, is more like 370 times the distance to the moon.
And he thought that the sun was 7 times bigger than the Earth, when in fact it is 109 times bigger. Even with that lousy measurement, Aristarchus was the first to make a really important conclusion, which is that the sun did not revolve around the Earth. The sun is 7 times, well, he thought